knows. We were almost sure, even they might not show up. But yeah, let's get started. So this is us in front of the Smith & Nephew office. We had gone to visit recently. Questions? So we'll start off with a recap of the use case very quickly. Don't worry, I won't show any graphic content this time. Our project is Technica, and it is a system designed to assist a surgeon with total knee replacement surgeries by autonomously drilling into the patient's bone. Just a reminder of what needs to be done. In case of a total knee replacement, an implant needs to replace the bone. And to fit that, the surgeon needs to shape the patient's femur and tibia in order to fit the bone. Based on feedback from our previous presentation, here are some definitions that we refer to throughout our presentation. So one is workbench. When we say workbench, we mean the operating table where the patient is, or in our case, the table where our bones are mounted. The surgical site is the location of the femur and tibia where the robot needs to drill into. These are some additional definitions that come on during the presentation. This is more technical. We have pre-stored bone models, which is a generic bone model in STL format, which we register the actual bone to. Drilling pose is the location of where the pins need to be placed. That is the location XYZ and the angle at which they need to be in for the surgical guide to come in for the cuts later on. Pre-stored surgical plan is the drilling pose on the STL model. And bone movement is any subtle movement during drilling or, well, if the patient moves, even involuntarily. Quickly, our use case diagram. In the procedure for knee replacement, we imagine a surgeon would start the process by orienting the patient in flexion, cutting the tissue and retracting it, exposing the bone. That's when our robot, our system would be wheeled in. Our system would analyze the bones, the environment, register it to the plan that we have, and decide where it needs to actually go ahead and drill in the real world. It will do this while compensating for any motion and drill holes in the femur and tibia. At this point, the surgeon can remove the system out of the OR, continue by placing the pins and the guide, and cut and shape the bone for the implants. Kimmy. Oh, before system level trace study. As to why we decided to make this system assistive and not fully replacing a surgeon, and as for why we need a robot in the first place, we came up with this straight study where we factored in safety, accuracy, usability, and by this we concluded that an assisted form is better than a fully replacement of a surgeon. Coming to the requirements.
Sorry. Okay, thank you so much, Ron. So based on all the feedbacks and the concerns we have received since our last presentations, especially those comes from the 4 boxes sitting at the corners here, not only did we modify our requirements that's closest to all the ongoing existing technologies, like what we did to the MP1 here, but also we modified them to show all the necessary details of our desired system's performance. For example, here for the MP2, we separated it to better show the process of the workspace capturing. Also for the original for MF4s, what we desired at first is the desired information. Now, including the pose and depth, are given separated. The rest of them are all the same as before. Yeah, as for our desired non-functional requirements, now we focus on the system's standard safety extendabilities and the minimals, that is the ease of use extendabilities. They are given separately in again. As for our functional architectures here, as you can see here, our first 2 inputs is a pre-operated bone model as the patient bones. We sense them, we register them, and obtain the desired drilling information we want. We use them to generate the desired trajectories with this trajectory, we move the end effectors to drill size, and then we visualize our final goals to drilling goals. Also, with the second cameras, we sense the surgical sites as another point clouds. With this, we visualize the obstacles avoidance. Also can be used as the visualized outputs. In coordinate functions with the physical change INO, it allows us to visualize the e-stops. For our subsystem trade studies levels here, as you can see here, the choice of the camera selection is the most important part, because several choices here. In order to make the right choices, we look back our sensing scenarios. The first cameras we use is to sense the bone mold shape, which is mounted on the arm. So we wanted to range sensing with high resolution for better point clouds. And the second cameras we are using here is to sense the surroundings. It's the top view camera. We wanted to visualize the avoid collisions. Therefore, we wanted to equip with the large FOV and the fast FES. With all these criteria, we look back at our arm mount cameras. So our choice for the arm mount camera is basically the RealSense D405, where we focus on the minimum depth, the point cloud qualities, and depth resolution. As for our top view cameras, what we concern most about is FPS and the point cloud qualities. So we finally chose the RealSense D435. As for the manipulator, give it back to Abhishek.
Right. Coming to the manipulator, our sponsors were kind enough to provide us the choice between two options, the Kinova Link 6 and the KUKA LBR Med. Now, considering our project is very manipulation heavy, this is arguably one of the most important decisions we had to take. So we put a lot of thought and consideration into this, and we came up with a very comprehensive trade study, which follows a very scientific approach. And based on this trade study, the Med 7 won by an overwhelming margin, as you can see. No, but on a serious note, we did do a proper trade study. When you think of the term medical or surgical robot, the first thing that comes to your mind is its precision or repeatability. And secondly, what price point are you paying to achieve that level of precision? But in our case, well, it's pretty much the same, so that is not a factor. And when it comes to cost, again, our sponsor is kind enough to provide us with a robot, so even that is not a factor. So what are the actual deciding factors? First is the DOF. So the LBR7 has 7 degrees of freedom. It has a redundant joint. That means it's more flexible, and considering our project is drilling in a very, it's about drilling in a very constrained region, that extra maneuverability is always desirable. Second is software support. You can have the greatest robot in the world, but it does not matter if you cannot effectively interface with it. So we did a bit of a literature survey. For the Med 7, we found an unofficial ROS package that's maintained by King's College. It's called the URDF, the ROS2 package, move it config and everything. We were even able to get it up and running. On the other side, for the Kinova Link 6, we barely found anything, or we have terrible Google skills, I'm not sure. The best thing we could find are the CAD files. That means if we want to use this, we'll have to make our own URDF, make our own move it config, and so on and so forth. We also talked to Hipster, and they mentioned they had some problems with the Cortex API when working with the Gen 3. So based on all these factors, we decided to go with the Med 7. Coming to a cyber-physical architecture, this is the high-level overview of what it looks like. We have divided it into ways. The main modules such as perception, actuation, control, etc. We have derived this from a functional architecture, and you will notice the color scheme will be maintained throughout our presentation. So if I were to walk you through this, for input, we make the distinction between the surgical I/O, and which is something that happens real time, such as the e-stop or the visualization. The things in the input block are pre-computed. These are provided to us by a sponsor, such as the preoperative bone model and the surgical plan. Coming to our hardware, the reason we've included this in the diagram is to better help visualize our actual setup. As you can see, there's the workbench, there's the manipulator, the way the two cameras are connected, one on a mount, one at the end effector, and we will also have a bone setup. From these cameras, we come to our perception module. So we have the D435 that just captures the top view point cloud. which is mainly to get an occupancy grid that goes into the planning scene for Move It. D405 is the real MVP here. It's hard carrying everything because that's what's actually used for registration, using which we obtain the bone post. And combine this with a pre-operative surgical plan, we then acquire the global drill flows. For planning, Move It is at the center of everything. We did talk to Hipster and they suggested there may be scenarios where you might find Move It a bit restrictive, but for right now, we decided not to reinvent the wheel and decided to go with Move It. So everything flows into it, the planning scene, the global drill flows, the pre-operative bone model, and based on this, it generates a trajectory that goes into a control stack. The trajectory goes to an OS2 control, which goes into the LBR server, which is an app that runs on the KUKA robot that actually actuates the motors. The same trajectory is also given to the drill controller, which controls the Dremel attached to the end of our robot via GPIO. So yeah, now we'll move on to the work breakdown structure.
So with our cyber-physical architecture is defined, we can come up with our work breakdown structure. So as you can see, we derive our work breakdown structure into 7 subsystems, and 5 of them come from cyber-physical architecture. So the first one is hardware setup. We must have to have a workbench for us to mount our arm, and also the synthetic bone model for our testing usage. And also we'll have to obtain our cameras. And after we obtain our cameras, we can design and build our own camera mounts. Either it's on the arm or it's on the workbench as a top view camera. And then after we finish the cameras, we can move on to set up the manufacturer. So for now, our decision is to grab a off-shelf drill, and we somehow hack into it. We design our own PCB and design our own drill mount to mount that drill onto our manipulator. And for the perception part, we'll first need to derive a camera calibration pipeline, and we will compare different methods. Either it's using a checkerboard or it's using a AirProtect to calibrate our cameras with our arm. And in the end, we'll come up with a better calibration pipeline, and we'll want to automate it. And as for the motion tracking, is to track the bone motion. We will design our motion tracking method and implement it afterwards. And for the registration pipeline, it's the most crucial part in our system. So first, we will try the most general thing is ICP. And if it does not come up with our performance requirements, we'll later try a newer method. It's called teaser, and hope you will have a better performance. But if it's not working again, we'll try to implement our own learning-based registration method. And so when it comes to planning, actuation, we will first have to set out a KUKA with ROS2, and we will try to find out trajectory planning algorithms from Move It, and we will compare and try to find the best trajectory generation method for us. And for actuation, because as I said, we use off-shelf drill, we need to modify it. So we will have to design our own GPIO with the drill, either it's in Arduino or other stuff. And when it comes to the surgeon input and output, there will always be a e-stop for safety concern. And we will also visualize the entire surgery process, either the state of the arm and the plan for the surgical plan. And we will also give some basic commands for the surgeon to direct the manipulator to the home position or stop the manipulator if it wants. And for the management, there's 4 crucial aspects in the project: work, finance, and schedule and risk. And we will also have a unique branch for system integration and testing. So after we done with each subsystems, we will test them one by one. And after they are all tested, we will try to integrate these subsystems together. And after the entire subsystem integration is done, we can try to test our system from end to end. And here comes the schedule for milestones. I'll hand it over to Shivamdi.
Honestly, I'm not the best person to talk about schedule considering how late I submit all my assignments, but I'm going to give it a shot. So, our milestones are based on the SVD and FVD. On a high level for the Spring validation demo, we are targeting one happy end-to-end flow, right till drilling the hole. Our first milestone is towards the end of January, having our workspace set up with the camera set up, the arms set up, everything. By the end of February, our end effector design with the drill mount should all be done. And parallelly, throughout this time, we'll be working on the controls and the perception. Both of these separate subsystems should ideally be completed as a milestone in the middle of March, so that between March to April, we have about a month to focus on integration and a bunch of errors which keep coming up, all of those testings. So that will be our final milestone for the Spring validation demo. Then for the fall validation demo, we'll optimize our happy flow much more by adding the visualization, the input from the surgeon, and then secondly, adding the dynamic compensation so that in case there's any bone motion, we're able to modify a trajectory accordingly, and reaching the actual accuracies that we have defined in our functional and performance requirements. So this is the Gantt chart that we've created for our Spring 2024 semester. So as you can see, initially we start off with a lot of the mechanical setup. It's in purple, all of the hardware, because you can't begin anything till the cameras and the arm is ready. After that, we have like parallel flow happening with different colors. So throughout February till mid-March or so, you can see where our milestones are to complete the parallel flows. And once that is done, we have a lot of the yellow where it's just integration and testing till we're complete by the Spring validation demo.
And for this fall semester, where we have for our FED, it's more of optimization and trying to meet the performance requirements. And this will of course get modified based on our progress till the SVD. So this is more of a rough idea of what we would be doing in that direction.
Coming to our risk analysis. So the first risk is that our cameras are not accurate enough, as we have stated in our performance requirements. So in that case, you would not actually be able to drill effectively in the sites that we want to. We are working on mitigating that. So first, we did a lot of literature review to decide the two cameras that we did. We in fact spoke to Intel at the Pittsburgh Robotics Network as well to see if they have any suggestions. So we don't think this should happen. So the likelihood is a bit low. But even so, we have a more mitigation plan of recalibrating the cameras, adjusting the camera mount location, and just brainstorming alternate vision solutions if nothing else works. Our second risk is that the MRSD room's 3D printer becomes unavailable, which is something we learned while talking to our seniors. So this can definitely arise because the printer might break, or there's a lot of teams and everybody would want to use the printer. So in that case, our plan of action is to talk to Tim and work in the RI workshop. Otherwise, we can use a TechSpark printer, and we're also open to the possibility of purchasing a personal 3D printer if we feel like we need to print a lot of parts for our infector and our mounts. Third, the manipulator might get damaged, especially because we're actually transporting it from Smith & Nephew's office to ours. Tomorrow, actually, we're getting a manipulator, and then we're going to be using it for a year. There's possibilities of things going wrong, but for that we're hoping to follow all the user manual instructions to make sure nothing can go wrong. We've also secured a workspace B512 for us, where hopefully there would not be too much crowd that might cause something to go wrong. Fourth is the drilling mechanism is insufficient. So right now we've decided to just pick an off-the-shelf drill, just drive down to Home Depot in January and pick up a Dremel. But we're not sure if that would meet the requirements that we have. Unfortunately, there's no way of knowing until we actually test this out, because there's not enough literature about pressure to mount a drill just on Kuka. But that's why, because the price point is effective, we're planning to just go down and test it. If it doesn't work out, we will design a custom drill. We've done a literature review for options for doing that. And we're also ordering our synthetic bone models over the winter. So as soon as we get the drill, we'll be able to test it. Finally, our robot might do the opposite of what it's actually intending to do and injure somebody. We really don't want that to happen, but it is a risk we should account for. So because of that, we have our entire subsystem dedicated to make sure that emergency stop is working, a physical emergency stop button. We design, build, and extensively tested to make sure that in case of any situation where the robot is losing control, all actuation to the manipulator as well as the drill would immediately cease. We'll follow the drill's user manual guide. We will keep all the demonstrations a safe distance away so that the drill can't harm anybody, and also keep a first aid kit ready, which reduces our likelihood really, really low. Yeah, that's it. Thank you, and break ahead.
Yeah, thanks, great job. One comment first on the 3D printer. We do have a Prusa now, which is reliable. I don't know if you guys have a chance to use it already. So one, I'll maybe try to buy a second next semester if I can avoid the slings and arrows from the business office. And then my question is just, how are you guys going to measure the accuracy of the drilling that you talked about?
So the only metric that Smith and Nephew gave us to check that they expect from us is that they want the drill to be with an accuracy of 2 mm and a 2-degree variation. So we basically know where we want to drill. We'll probably just draw a dot, see if it actually does that. We have it on the software. That'll be for our deviation with the.
Just to add on to that, what Hipster used to do was that, so theirs was reaming, basically. So there's the handy scanner, which is a very expensive piece of equipment, so we can't bring it here. So they would ream the pieces, they would go to Smith and Nephew's office, get it scanned, and compare it with the plan, and then compute the error. So that is one.
So you're going to scan it offline, I guess. So I'm wondering, apart from the standpoint of how you're going to do validation at SVD and FVD, does it require making the hole, drilling the hole, and then you have to take it somewhere and do the 3D scan in order to kind of figure out what you have to do?
I think that was the criteria for the final FAD. For the SVD, they were just directly reaming it and seeing if it's like basic eye test, basically. That's what they were doing. So.
Okay. So the scanner is only available at Smith and Nephew's?
Yeah, it's actually a very expensive piece of equipment. So we asked about it, they were like, no.
We initially asked if we could actually mount it on the robot because it's very accurate, but they said no.
All right, sounds good. Thanks.
So with Smith and Nephew buying graduation system, so you guys have is there a case study on that? Where are you guys at with that?
Yeah, so we did a drill study about whether we should take an off-the-shelf drill or add a custom drill. We didn't add it here, unfortunately, due to like time constraints. But because designing a custom drill would take very long and might not even work at the end, it's much more effective to purchase an off-the-shelf drill. It's just $25, and we can, if that works, then we're saving a lot of time to like actually design a drill. So we're just going to purchase that from our budget. And if that doesn't work, we have some like basic outline and plan to make our own drill as well.
So we talked to Hipster, and they had designed a custom end effector. And we asked them why, and they said they did it for the learning experience, not because their project actually required it.
And are there any concerns with using an off-the-shelf drill like other medical drill?
Yeah, so that's also what we asked, whether we should use something like a striker's medical drill, which is more surgical grade. But they said not to waste our like money on that, and that's not something we should like worry so much about. Like, so Branko was happy to like let us use any Dremel from Home Depot.
Okay. I noticed you had something which is called the IK solver.
Yeah.
What is the IK solver?
So the inverse kinematics solver.
Oh, the inverse kinematics.
Yeah.
Okay. And it's just stood in there, the architecture and so on. What is
I think it went connected to MoveIt because
Okay.
MoveIt uses an IK solver.
Okay.
It uses KDL by default, which is a numerical solver, which is normally good enough. But in case that's not good enough, we can always switch to an analytical solver with IK fast.
I had to ask about IK, what is exactly? Because you have FK in there. So I'm not sure whether you can listen, that's why I want to make sure. Okay. All right. Will Smith and Nephew provide the KUKA, or do they have a KUKA right now?
Yeah, we're getting it tomorrow actually.
Okay, that's great. Then one of your packages, 1.52 is visualization. You don't have to go to it, but it's the visualization. So are you doing the visualization, or what does it entail for the surgeon?
So I think we had also explained this last time. It's just a very basic visualization with like 3 buttons on it for start, stop at home, and all it does is it has a camera feed, and what the trajectory of the robot is going to be. In case something is wrong, you can shut it off.
Okay.
So what the bot is going to do next, it just comes on that. So just for safety purposes.
When you visit the Smith & Nephew office, their user interface is very simple. It's very simple because they used to control them with foot pedals. So it can't be too complex anyway.
Now the role of Chris will talk about it, how you're going to demonstrate setting up, the scanning and everything. So we'll talk about all those things. But thank you. All right, great talk.